Okay, so get this. What if the future of artificial intelligence isn't actually here on Earth at all? What if it's out there, among the stars? Now, I know it sounds like pure science fiction, right? But a brand new research paper from Google lays out this surprisingly plausible roadmap. So, let's dive in and see how they think we can actually pull this off. The whole idea really, it starts with this simple but kind of provocative question. Is Earth actually big enough for AI? I mean, with its explosive growth, is our planet going to be able to contain it? And according to this research, because of our physical limits, the answer might just be no. And it all boils down to one single critical resource. And yup, that resource is energy. You see, even though AI models are getting way more efficient, the sheer volume of how much we're using them is just growing exponentially faster. And that's creating this absolutely massive and frankly pretty unsustainable demand for electricity to power all of our data centers. So, first up, let's really get a handle on this foundational challenge. We're talking about AI's unstoppable thirst, that hidden cost of computation. Okay, check out this number. 3.86 times 10 to the 26th watts. I mean, what even is that? Well, that is the total power output of our sun. And to put that into perspective, it is over 100 trillion times more energy than all of humanity's electricity production combined. So, yeah, if AI needs power, that is the ultimate untapped source. So, if the ultimate power plant is just hanging out there in space, why not move the factory right next door? And that's exactly what brings us to this incredibly audacious idea, putting a data center right in orbit to tap that ultimate power source. And this quote from the Google research paper it nails the core idea. It says, instead of transmitting power to Earth from space, we propose a future that includes space-based ML data centers. You see, for decades, people have talked about beaming solar power down to Earth, but it turns out that's incredibly inefficient. This idea, it's a complete paradigm shift. Don't bring the power to the computers, bring the computers to the power. And when you compare solar power on Earth versus in space, the benefits are just staggering. I mean, down here, you've got the day/night cycle, you've got clouds, weather, the atmosphere getting in the way. But up there, in what's called a sun-synchronous orbit, a satellite is always in sunlight. You get nearly continuous 24/7 direct power. The paper estimates a solar panel in space can harvest up to 8 times more energy per year than the exact same panel here on Earth. And the best part, it doesn't use a single acre of land or a single gallon of water. All right, so the why is pretty compelling, right? But what about the how? Well, that's where we get into solving the space puzzle. The paper breaks it all down into the 3 biggest technical challenges we've got to overcome. And this first one is a real head-scratcher. How do you build a supercomputer with no wires? Seriously, think about it. A modern AI supercomputer is this dense web of fiber optic cables connecting thousands of chips. How in the world do you replicate that between dozens, maybe even hundreds of separate satellites, all flying through the vacuum of space? Well, the answer is a technology called free space optics, or FSO. And you can pretty much think of it as creating a wireless fiber optic network, but using lasers instead of cables. These laser links would beam data between the satellites, basically creating that super high bandwidth connection, that inter-chip interconnect that you absolutely need for large-scale AI. But, of course, there's a catch. Like any signal, these lasers get weaker the farther they have to travel. And to get the kind of bandwidth we're talking about, around 10 terabits per second, to match what we have on the ground with physical cables, you need a really strong signal. So the proposed solution? It's simple in concept, but absolutely mind-boggling in practice. You have to fly the satellites extremely close together, within 300 kilometers. And yeah, flying that close immediately brings us to the second massive challenge. To stay connected, these satellites would have to perform this constant, incredibly precise cosmic dance, all while making sure they never ever collide. So, just how tight is this cosmic dance? Well, the paper models a cluster of 81 satellites, all flying in a formation with a radius of just 1 kilometer. That means the distances between neighboring satellites would be constantly shifting, somewhere between 100 and 200 meters. That is incredibly close. And really, the only way you could ever hope to manage that is with super sophisticated ML-based slight control. Okay, so we've got a plan for power and a plan for connectivity. But what about the actual brains of the operation? I mean, can the super advanced commercial AI chips that we use right here on Earth, can they even survive the harsh radiation of space? This was a huge question mark going in, but the test results are actually incredibly encouraging. Researchers basically took one of Google's Trillium TPUs and just blasted it with a proton beam to simulate what it would go through over a 5-year mission. And guess what? The chip survived the full dose with 0 permanent failures. In fact, the most sensitive part of it, the high bandwidth memory, it only started showing issues after getting nearly 3 times the minimum required dose. So the big takeaway here is that we might be able to use commercial off-the-shelf hardware. We might not even need to design special space-proof chips from scratch. Okay, so the technology seems plausible. The engineering puzzles have solutions. But this, of course, brings us to the giant elephant in the room for any space project, the price. We're talking about getting this whole thing to orbit affordably. It's the first question anybody asks, right? But isn't launching stuff to space just impossibly expensive? And you know what? For most of history, the answer has been a resounding yes. So what's different now? Well, it all comes down to this magic number that the researchers identified, $200 per kilogram. That's the target price to launch something into low Earth orbit. Why that number? Because at that price point, the math shows that the annualized cost of launching your power source into space becomes basically the same as just paying the power bill for a data center down here on Earth. And the only reason we can even talk about a number like that is because launch costs have been absolutely plummeting. Reusable rockets like the Falcon 9, which costs about $1,800 a kilogram, completely changed the game. But the real game changer, the one everyone is watching, is Starship. It is being designed from the ground up to push those costs well below that critical $200 per kilogram mark. Now look, this isn't going to happen tomorrow. The paper's own analysis suggests that we'd need a really sustained high launch rate. We're talking something like 180 Starship launches a year to hit that target by around 2035. But the trend is clear. The economic trajectory is absolutely heading in the right direction, and in the far future, with extreme reuse, you could see costs drop to as low as $15 a kilo. It's wild. So, let's recap. The biggest hurdles we talked about: connectivity, that cosmic dance of orbital mechanics, radiation survival, and even cost, they all seem to have plausible solutions on the horizon. So, what's next? What does the road ahead look like? Oh, don't get me wrong, there are still plenty of other hurdles to clear. For one, thermal management. How do you cool these incredibly power-dense, hot-running chips in the vacuum of space? That's a huge problem. Then there's ground communications. You still need to get the data to and from Earth at high speed. And maybe most important of all, reliability. These systems have to be ridiculously fault-tolerant because, you can't exactly send a repair person up there if something breaks. But as the paper itself concludes, these results are an incredibly encouraging first step. What they do is show a milestone, a feasible, engineering-based path that could actually get us there. So this isn't just some wild science fiction idea anymore. It's a moonshot for sure, but it's a moonshot with a plan. And all of this leaves us with one last really fascinating question to chew on. For all of modern history, we've brought the world's resources to our computers. But what happens when we finally start bringing our computers to the universe's resources? So if compute moves to space, what else is going to follow it?